Oh, so yeah, let's get started. So today we are going to briefly recap the things that we discussed for the DDPN, and we're going to move on to the diffusion models. So last week we started to discuss the basic ideas about the diffusion models, which was basically having some key characteristics. The first one is that we are defining both the forward and the reverse the processes as some kind of the sequential the processes. And also the thing is that the forward process is not learned, but it was kind of some predefined some kind of the procedure, right? And also we started to match basically dimension of the latent variables and also the input data this is kind of some characteristics. And specifically for the DDPM, what also we have seen is that we specifically define the forward and the reverse processes, that's the Markovian processes. And also the forward transitional distribution was defined into this specific form, into this Gaussian distribution. So the meaning of this was basically that we are gradually adding some kind of the noise into the data points while we are increasing the variance in the Gaussian distribution. So this was basically the key characteristics of the DDPM. And today we are also going to start to basically discuss some kind of the non-Markovian processes as well. And once we basically define this like forward transitional distribution in this way, then now we could also derive the other two conditional distribution, which was the first one basically the forward jump, basically sampling the xt directly from the data point of the x0, which is another the Gaussian distribution. And also the conditional distribution, like sampling xt minus 1 by conditioned by the xt and the x0 was also defined into the Gaussian distribution. Into this specific form. And we also introduced the term of the epsilon t, which was basically the noise that has been used to sample the xt from the x0. And the mean of like this specific the posterior distribution could be also derived, basically defined not only using the xt and the x0, but also using the xt and the epsilon t. So the goal of basically the training of the neural network was to basically match this variation of the likelihood distribution to be the same with the distribution in the previous slide. So in terms of that, there could be basically three different ways in terms of training the neural network. The first way was to basically make a mean predictor, which is directly predicting the mean of the specific the variation of this distribution. And the other way around was basically not directly predicting the mean, but actually predicting the x0, the original data point, and then basically computing the mean using both the xt and the prediction of the x0 here. And the other way around was also not directly predicting the x0, but also predicting the epsilon t. In terms of that, now we can also compute the mean using both the xt and the predicted the epsilon t. So there could be basically three different ways that we can make some the DDPND model in terms of like trained neural network. And the interesting thing is that whatever the predictor that we have, all the loss function basically coming from the elbow, the formulation, basically came down to this kind of specific, very simple the L2 the loss function. So that is basically giving some kind of one of the key advantages of the DDPM and also the diffusion models in terms of that we're having some very simple the training the loss function. So everything just becomes some kind of the L2 loss like this, right? So in the first assignment, the goal was specifically to implement the noise predictor. But it could be basically having some kind of the other predictors like XU predictor and the mean predictor. And also, I recommend you to try to basically modify the code of the assignment one in terms of like switching the predictor into the X0 predictor and the mean predictor and see what happens in practice. But theoretically, these three are like all identical things. But in practice, there can be some kind of some differences in terms of the performance. So you can check that out yourself. So as you can see, the loss function here is basically defined as kind of the expected value over the time t and also the x0 and the xt samples from this specific distribution. So what we can do in terms of training the neural network was basically just like minimizing that expected value. That we are sampling the x0 here and also sampling t here and also sampling the xt from this specific the posterior distribution. And basically running the backpropagation through the L2 the loss function in terms of like minimizing the specific the loss function. And in the generation D time, the procedure also is kind of the sampling in terms of that we are starting from like sampling from the prior distribution, which is the standard, the Gaussian distribution. And over time, now we are sampling the XT from this, the variational, the likelihood distribution. Basically by computing the mean from the noise, the prediction, and also like sampling the XT minus one in this way. So this was basically what we discussed in the last week. And so this is also what you need to do. You need to implement in the first assignment. And here one quick quiz is that, so in this slide, we are basically seeing like how we can compute the mean of this, the likelihood, the distribution from the given the XT and the prediction of the noise here, right? Then like instead of like the mean here, can you also compute the prediction of the X0 from the given the XT and the prediction of the noise? Can you quickly basically derive the formulation, which is computing the X0, not the mean, from the given the XT and the epsilon here. So let me give you like a couple of minutes. Yeah, so as most people also post the answer in the Slack, the answer is this, right? So if you don't know how exactly we can derive this, I recommend you to check out the details in the DDPM slides again. And these are basically the formulations that we're gonna keep dealing with in the rest of the all the entire class. So we're gonna keep seeing this kind of these formulations of the DDPM, the DDIM in the all the other lectures. So if you are not sure exactly how we can derive this kind of things, you will need to check out the more details with DDPM. And yeah, so what we can also see as kind of our diversity process is like kind of this. So we are basically, for each of the step, we are having the XT, which is the noise data point. And given this, like we are predicting the epsilon, which is the noise. And based on that, we are first predicting the X0, which is kind of the best prediction of the final data point from the given the XT, the noise data point. And we are not directly taking this. We are basically using this information to compute the mean of the likelihood distribution and sampling the XT minus one and repeating this process. And from this, like what we can see is that this is kind of the process is basically we are basically defining the prediction of the X0 over time. So as we also have seen in the previous lecture, we can see that this the prediction of the X0 will be basically gradually improved over time through this kind of the denoising the process. So it might be also basically interesting to basically visualize this prediction of the X0 every step in the assignment one in terms of like you are seeing that the X0 is basically defined every step. Yeah. And before we move on to the next the topic, also one important question that we might also need to discuss at this point might be this. So from the next week, we're gonna also discuss some kind of the practical ideas in terms of how we can train these diffusion models with the billions of images. So literally in the internet, we're gonna have some like more than billions of images. And the question might be is that how we can also train the diffusion model with this kind of like billions of images. But also the question might be is that like if we have really like tons of the internet scale of the images, then do we really need to generate the data using the diffusion models? Maybe we can just directly sample one of the images that we have in our training data set. Then one of the advantages like having this kind of the generative model in terms of like directly using one of the images in the internet. So this is also like important question that we need to think about. So let's quickly think about like this question for another couple of minutes. Yeah, as most of you are posting the good answers, there can be still like a bunch of the advantages in terms of like having the diffusion, the generative models. So basically, like one of the advantages like having the generative model is that we don't need to basically have the all the billions of the images in our storage. Basically, if we train the noise predictor and all the one of the predictors that we discussed, that will be the case that the neural network is basically encoding the information of the entire data distribution. That means that our network basically has the information about the billions of images and basically compressing that all the information into the neural net parameters. So in terms of that, we are compressing all the information into the neural net parameters. There can be some kind of advantages in terms of the efficiency and the scalabilities. And also the thing is that our general models will be able to produce some of the images that are not really presenting in our training data set, but they are basically not exactly the same, but still some kind of the realistic and the plausible images. So in terms of that, we don't need to rebuild the images in our training data set. So we can basically somehow protect the privacy issues or some kind of copyright of the information that we are having in our training data set, while making some of the some kind of the realistic some of the images or some kind of data points. So in terms of the privacy and the copyright issues, there can be still some advantages like having our some general models. And also from the next week, we're gonna also start to discuss some kind of the conditional setup, like the text to image generation or something to image generation or something. For those kind of the conditional setup, like directly using some of the samples in our training data set, will become solving the retrieval problem. So given the query information, what should be kind of the output that we need to basically retrieve from our kind of the given the data set. So comparing to this kind of like solving this kind of retrieval problem, basically the conditional generated models will be more efficient in terms of that we can basically very easily generate some kind of the new data points from the given condition. We can also start to discuss this kind of the conditional models from the next week. So, but also this basically also shows that depending on the applications, there can be some of the cases that we don't need to actually train a generated models. It can be actually better to solve some kind of some retrieval problems in some specific situations. So depending on the applications that you are dealing with, which you might need to also consider whether it's really kind of good to have a generated models, or you can also consider directly using some of the samples in the given the data set. So this is also kind of the important point in terms of like how we're gonna utilize this kind of the ideas of the generated models. Okay, so now let's quickly move on to the today's topics. So for today, we are going to discuss the two topics. Like one is about like seeing the connection between the DDPM and also the score-based models that we are going to discuss for today. And we are going to discuss another the diffusion models, which is the denoising the diffusion implicit models, which is called the DDIM. So let's move on to the score-based models. So before we discuss the score-based models, what's the score? So what's the meaning of the score? So the meaning of the score in the statistics is quite not the kind of the things that we are typically saying. Basically, here the score means that it's the gradient of the log likelihood of the function with respect to the data points. So if we have some kind of the PDF, the probability density function for the data points like this, if we take the gradient of the log of the probability density function, basically taking the gradient with respect to data points, then this becomes the score. So this is the meaning of the score. So and we're gonna use this term for many of the rest of the lectures in this class. So please keep in mind of the meaning of the definition of the score. And also we're gonna see how this score is related to like what we have discussed so far in this class. So what we are going to see is that, so we're going to first see how we can compute the score of this specific, probably the distribution, the posterior distribution, which is about the fold jump, right? Sampling the xt from the x0. So given this kind of the posterior distribution for the fold process, how we can define the score function. So this is the first thing. And the second thing is that we're going to see how this score is basically related to basically the noise that we are predicting using neural network. So actually, we can directly calculate this score because we know that this distribution is basically have this kind of specific the form of the Gaussian distribution. So given the definition of the Gaussian distribution, actually we can directly compute the gradient of the log of the PDF, then we can see that the score becomes like in this form. So you can see that this is the form of like taking the log of the PDF of the Gaussian distribution. And if we take the gradient over this, then we get basically this, right? So this is the nothing based on the definitions that we have seen. And from this, like what we can also see is that from our the definition of the epsilon t, which is basically the noise that has been used to sample the xt from the x0, now we can see that the score function of like this specific distribution actually becomes like the same with the noise, but scaled by this scaling factor. So you will basically need to remember this kind of the relationship between the square of this distribution and also the epsilon t here. So from this, actually, what we can see is that, like, we are basically training the noise predictor for the DDPM. And now we can interpret the meaning of the noise predictor is basically predicting this core function for this basically the posterior distribution up to the scaling factor. So we don't obviously have this kind of scaling factor, but we are basically predicting this epsilon t directly. But we can consider that actually the predicting the epsilon t is basically identical with basically predicting the score of like this probability distribution up to the scale factor. So we're gonna basically see this kind of a relationship in those of the rest of the lectures. And also, is this clear? Any questions on this? And also the interesting thing is that we can derive the same formulation using the Tweedie's formula. So Tweedie's formula is basically some kind of the interesting formula in terms of like showing that. So let's think about the case that we are having some kind of the probability the density function, which is known as like the Gaussian distribution. What's the so yeah, there has been some kind of the update in the slides. So I will also update the slides after the lecture. So yeah, but the meaning of the Tweedie's formula in English is that, so let's think about that we are having the Gaussian distribution, but we don't know the mean of that distribution. The only information that we know about that the Gaussian distribution is that the fact that that distribution is a Gaussian distribution. And let's we also know the variance and some of the samples that are samples from that distribution. But let's say we don't know the mean of the distribution. Then the question is that given the samples and the variance, how we can also get some kind of the expected value of that mean of that the distribution. So what the Tweedie's formula says is that if we only have the samples and the information about the variance, given this information, we can have the expected value of the mean into this formulation. So basically, if we only have the samples and then the variance here, then we can calculate the expected value in this form with some kind of the derivation. And if we have this kind of the formula, then we can derive the same kind of formulation that shows the relationship between the score and the epsilon t here using this kind of the Tweedie's formula here. So what we can see is that we know that the mean of that distribution should be this, right? So the expected value of the mean is basically known as like this. And from the Tweedie's formula, we can see that this should be the same with this formulation, which is basically involving this score here. And if we rewrite this formulation, then now we can derive the same formulation showing the relationship between the square of this function, the probability, the density function, and also the epsilon t here. So from this, we can see that the noise prediction is basically the same as predicting the square of this posterior distribution. How do you get the derivative of log p if you don't know the mean in the Tweedie's formula? Well, yeah, so we can obviously compute the this is basically showing the relationship between the score function and the other the parts of the terms here. So we can also get into like how we can also compute the score for some kind of the given distribution. So yeah, this is basically about showing some kind of the relationship between the samples and the variance and the score that can be used to basically compute the expected value of the means. So here the question might be also like, why do we care about this score? So what's the meaning of like having some kind of the information about the score function? So that's kind of one of the main things that we are going to discuss today. So let's recall like what we have discussed in the lecture 2. So what we discussed in lecture 2 is that if we basically have the information about the distribution, the probability density function for the distribution, then we can sample from it, right? Sample from the distribution. So we have discussed some kind of some techniques that we can use in terms of sampling some of the data points from the given the probability distribution. And here the interesting thing is that if we have the information of this core function, not exactly about the PDF of the probability distribution, then without basically knowing some kind of the information about the probability distribution, even just using this core function, we can still directly sample the points from the given the distribution without having the explicit the PDF the function. So that's kind of the technique which is called the Langevin dynamics, which is coming from the physics. And the basic idea about the Langevin dynamics is very simple. So the way that we are sampling the data points, even without knowing the probability the distribution, but only using this core function, is basically this way. So there are basically several steps, but you can say that the basic idea is that we are sampling some of the data points from some kind of the prior distribution, which is typically also the standard Gaussian distribution. And starting from some of the samples from the prior distribution, we can just simply iterate this process. You can see that this is basically nothing but from each of the data points, we are adding some kind of the score with some kind of the weights, and also basically adding some kind of the perturbation with the standard Gaussian noise here. And what is basically guaranteed in this formulation is that when the weights of this core is getting close to zero, and if we basically iterate this process for the almost infinite time, then we can see that the data points will basically converge into one of the data points of the original data distribution. So this is basically the procedure of the Langevin dynamics. So you can see that this is kind of some very interesting way that we can sample the data points even without having the information about the probability distribution, but only using this core function. It is clear? So you can see that actually this is kind of similar. It's like what we are doing in the reverse process of the DDPM. But we can also clearly see some kind of the connections between the DDPM and this procedure. And this is the some of the animation showing some kind of how exactly the data points are basically moving to the some kind of distribution. So you can see that at the very initial stage, the points are basically almost uniformly sampled over the space. And as time goes on, you can see that the points are basically moving towards to some high density regions in here and here. Question here was does the waiting time change over the T steps? No. So it also depends what sort of the waiting time that we use. But yeah, we can vary this wait time. We can also use some kind of some constant wait time here. But when you see basically the connection with this to the DDPM, then we can see that how this wait time is changed. Okay. So in terms of also encoding the information of the probability density distribution, what we can do is that we can basically train a neural network that can predict the score. So one of the ways that we can encode the information of the data distribution is to basically having this kind of score prediction network, which can be trained in this way. So in the case that when we can basically directly calculate the score here, we can train a neural network that is basically minimizing this L2 the loss with some kind of while basically calculating this kind of the loss as kind of expected value by sampling the points with given the data distribution. So we can think about making some score prediction network by taking this as kind of loss function. Right? It is clear. So we can see that this is also kind of similar with the noise prediction network. So here the question might be is that how we can exactly compute this score here, right? So let's say we only have some kind of the samples of the data distribution, but we don't know the information about exactly about the data distribution. And given this kind of situation, how we can exactly compute this score? So obviously for those kind of the cases, when we only have the data samples, we cannot directly compute this score here, right? So what we are going to do is that we are going to have some kind of the slightly perturbed the data distribution. Um, so let's say we are having this kind of this QX is basically our original data distribution, now which will be denoted as the QX0 here. And we are going to basically approximate this data distribution as kind of the mixture of the Gaussians. So what we can see is that now we are not directly taking the QX0 as kind of our distribution, but basically slightly perturbing each of the X0 with some kind of the Gaussian here. So which is basically the case that we are taking this Gaussian distribution as some kind of the convolution, the corner, in terms of making slightly some corrupted distribution. So this is kind of one of the visualization that we are having some kind of the 3 points here and adding some kind of the Gaussian, some the perturbation here in terms of like making slightly the corrupted the distribution. And we can also easily sample from this kind of the modified distribution. So the simple way that we can sample from this kind of the modified distribution is basically sampling from the X0, which is basically taking any of the random samples that we have, and then we can add some kind of the perturbation like this. Then this will become the way that we are sampling from the QXT here. Right? It is clear. So let's think about it now. We are training this core prediction network with this kind of the slightly modified distribution. And then we're going to have this kind of the objective function, the loss function here. And after some kind of the derivation, actually what we can see is that this becomes identical with basically predicting the noise for this kind of the conditional distribution, or the posterior distribution sampling xt from the x0 with some kind of the derivation. And now what we can see is that now training this core the prediction network here becomes the same as kind of the predicting the noise that we are basically predicting using the noise prediction, the network in the DDPM. So now you can see that this is not just kind of like similar with the reverse process or kind of the noise prediction network in the DDPM, but actually it becomes identical once you basically make some kind of the perturbed the data distribution. It is clear? So this is like coming from some kind of the relationship that we have seen between this core here and the epsilon t here. So then here the question is that how are we going to basically choose the kind of the variance for the perturbation? So we can consider like the controlling this variance here. So if we basically have some very small the variance here, the advantage would be basically that we are not corrupting the distribution that much. We basically have some kind of the distribution which is basically close to the original data distribution. Yeah. But here basically one downside is that basically we are having the loss function like this. So as you can see, we are sampling the data point x0 from the original data distribution, and basically for those samples, we are basically minimizing this L2 loss. So if we have this kind of some kind of the data distribution that has some kind of the high density in this region and the low density in this region, then what we're gonna have as kind of the output is that we're gonna have some very few samples that are sampled from this kind of the low density regions, right? And since we're gonna have some very few samples in these regions, we are not gonna basically train this kind of the score prediction network not that many times for those regions. But mostly the samples will be concentrated on this kind of the high density regions, right? Which means that our prediction for this core in these like low density regions will be not that accurate because we are not going to have that many samples in these regions. So that's kind of the downside, like when you have the small variance here. Most of these samples will be saturated on the high density regions, and which means that we are not going to have some kind of the good prediction for this core in the low density regions. So to avoid this kind of issue, what we can do is that we can simply just like increase the variance here in terms of having some more like the blurry distributions over the space. Then we can basically avoid having some kind of the low density regions and having some kind of the more like some kind of uniform, like some kind of samples over the entire space. But obviously in this case, the problem is that we're going to have some kind of the corruption, like more the perturbation from the original the data distribution. So the score that we are predicting may not be also not that close to the score of the original data distribution. So as we have some kind of the more the blurry some kind of distribution like this, we're gonna basically avoid having some kind of the low density regions. So in terms of we are having some kind of the more accurate the predictions of the score in the low density regions, but the prediction in the high score, high the density regions will also get inaccurate. So as you can see, there are some kind of the pros and the cons. So as we basically have some kind of the small d variance in the perturbation, the score prediction will become more accurate in the high density regions, but the score prediction will become less accurate in the low density regions. But compared to this, as we basically increase the variance in the perturbation, what we're gonna see is that the prediction of the score will get more accurate in the low density regions, but less accurate in the high density regions. So basically, we're having this kind of the pros and the cons. So what we typically do as kind of a solution for this is that we are varying the variance over time. So over the time of the roundabout dynamics the procedure, what we can do is that we can start from some kind of the high variance here. In terms of that, we can also have some kind of the good prediction in the low density regions, as you can see here. But after the few steps, we're going to see that the samples are like more concentrated on the high density regions. And now we will need to have some kind of the better predictions of the score in the high density regions. Then we are decreasing the variance over time in terms of that now we can get some kind of the better the scores in the high density regions and basically making the samples to better follow the given the original data distribution. So this is the technique which is called the annual the longevity dynamics in terms of that we are gradually decreasing the annualing the variance the perturbation in terms of that starting from the higher the perturbation and going into some kind of the lower perturbation. And you can see that actually this is exactly the same as like what we are also doing in the reverse diffusion process in the DDPM. So if you record like what we have done in the fourth process and the reverse process in the DDPM, in the reverse process, we started from some kind of the high kind of variance of the perturbation and going down to some kind of the low the variance of the perturbation. And the fourth process is the opposite. We are basically gradually adding some kind of the noise from some kind of small perturbation to the larger the perturbation. So you can see that the reverse of like this becomes the exactly the same with the fourth process of the DDPM. So again, like at the beginning of the longevity dynamics, we are starting from the large variance here. In terms of that we can have some kind of the better the predictions score in the entire space in a way that the samples can get closer to the high density regions. And once we basically see that the samples get closer to the high density regions, now we want to get some kind of the better predictions of the scores in this kind of high density regions. Then now we are gradually decreasing the sigma t here in the variance of the perturbation in terms of that we can get some kind of the better performance of the longevity dynamics. So as you can see, now we want to basically predict the score while basically varying the variance of the perturbation here, right? So which means that now we need to predict score for the multiple versions of the some perturbed the data distributions, which means that now we will need to predict score for the varying time t here. Now which becomes exactly the same with the loss function that we have seen for the noise predictor for the DDPM. So you can see that now the score-based model that we are discussing based on the annual longevity dynamics is basically exactly the same that we have done in the DDPM. So which means that the DDPM can be interpreted, the reverse process of the DDPM can be interpreted as kind of like the process of the learning the annual the longevity dynamics. It is clear? So yeah, you can see that this is like just another way to understand the DDPM, the reverse process, and also the fourth process. So the fourth process of the DDPM now can be seen as kind of like gradually adding some kind of the some perturbation while increasing the variance here, right? So this is exactly the same with the fourth process. So any questions on this? So also one of the questions here might be is that, so how many steps of the iteration that we need to do, right? So as also we have seen in the slide of the longevity dynamics, as we basically decrease the wait time for the score and also repeat the same process as more times, we're gonna get some kind of the better sort of the approximation of the original data distribution. Which means that also in the DDPM, as we have some more the time steps, we're gonna get some kind of the better the quality of the generation. So we can consider like having some kind of the infinite the number of the times of the iterations. Then that becomes some kind of the process that we are running this kind of process in the continuously time domain. How they schedule the variance to linear function. So yeah, scheduling the variance will be basically scheduling the beta term in the DDPM. So now you will be able to see the connection between the formulations between the score-based models and the DDPM deformulation. So the variance term in the score-based model was basically denoted as the beta in the DDPM. And we also have discussed like how we can schedule the beta, right? Using some, so in the assignment 1, you basically need to vary the beta term using some linear function, and you can also consider using some kind of cosine function, many other things. Any questions on this? Yeah, so if we basically have some like infinite the number of the times for the iteration, that becomes the kind of the things that we are running this kind of process in the continuously time domain. So we are not gonna get into some more details about this, but we're gonna come back to this point after some of the other lectures. But basically, roughly speaking, basically in the continuously time domain, like solving this kind of the annealed the Langevin dynamics actually become the same as resolving this kind of stochastic differential equation. So we can also discuss some kind of the connection between like the DDPM and the diffusion models resolving this kind of stochastic differential equation. So, and also what you can say is that not only the fold process, but also the reverse process is also formulated with another stochastic differential equations. And the DDPM actually basically can be considered as basically some sort of the discretization of the time domain of the SDD formulations. So which means that we can basically run the fold process and the reverse process by just directly solving the SDD formulations. And that's also what we are going to discuss after the midterm debate. Okay. So we are not going to get into some more details for this, but we'll get back to this point, like solving the SDE after some of the lectures. It is clear? Any questions? Yeah. So this was about some like seeing the connection between the DDPM and the score-based models. Is there also some connection to the transport maps between the different? Yes. So this can be also seen as kind of the optimal transport, basically finding some kind of some mapping between given the prior distribution to the data distribution. Obviously, this is the case like solving the optimal transport problem. So you can also get into this point after some of the lectures. Any other questions? So as you can see, there are lots of some kind of the theory and many interesting way to interpret the same diffusion model into the different angles, right? So we're gonna also see another kind of the aspect like seeing the DDPM into the different angles here in the DDIM. So here the kind of one of the main motivation to see the DDIM is that so we have seen some kind of the 3 different types of the generated models. Like one was the GAN, and the other one was basically VAE, and also now we are discussing the diffusion models. And some of the pros and the cons of like this model is that GAN was basically good at basically generating some kind of high quality samples and also basically fast in terms of sampling. But there has been some kind of the mod collapse issues in the GAN pipeline. And the advantage of the VAE is that it does not have that much of the mod collapse issue, and also it can also produce the samples quite quickly, but the quality of the output was not that good. So that's kind of downside of the VAE. The good thing of basically the diffusion model is that now it can produce some very high quality samples without like suffering from some kind of any mod collapse kind of issues. But the downside of the diffusion model is that basically the time for the generation is much longer. With some kind of the feedforward kind of neural network of the GAN and the VAE, because we need to run the noise prediction not only once, but we need to iterate this kind of the noise prediction multiple times. So for typical the DDPM implementation, the sample of the in the time domain is basically the 1,000, which means that we need to iterate this kind of the sampling the process 1,000 times, which will be very slow. So here the kind of the motivation is that how we can basically speed up this kind of iterative process in terms of basically generating the samples more quickly while still maintaining the good quality of the outputs. So that's the motivation of the DDIM. So for that, now we're gonna start to see some kind of the another kind of diffusion models, which is basically not using the Markovian the process. So one of the key features of the DDPM was that basically we are defining the forward and the reverse processes, and basically the Markovian the processes, right? And here the question is that can you also make some kind of the non-Markovian the forward and the reverse the processes? So if we get back to the DDPM, the forward process was defined like this. Basically, starting from the x0, like we are sampling the x1 from the x0, and also sampling the x2 from the x1, and repeating this kind of the process with the predefined the forward, the transitional distribution here, which is the conditional distribution sampling xt from the xt minus 1. Now we are going to switch the forward process in this form. So as you can see here, the meaning like this is basically that we are not having some kind of the Markovian process, but this is kind of slightly weird process in terms of that while we are basically running this in the forward way, the sampling becomes like we first sampling like x capital T from the x0, which is basically some kind of the final the output that we want to see, and then sampling all the kind of intermediate the latent variables xt in the kind of reverse manner. Basically sampling the xt minus 1 from the both the xt and the x0. So even you can see that even for the forward process, the sampling becomes kind of the reverse manner. Like starting from the x capital T, sampling the each of the xt minus 1 from the both the xt and the x0. Right. So this is kind of the new forward process, which is defined with this specific the conditional distribution sampling xt minus 1 from the xt and the x0. Okay. So then here the question might be is that, so how should we define this specific distribution? So as we have done so far, we are also going to use the Gaussian distribution. So let's define this specific, the conditional distribution as another the Gaussian distribution, which is also taking the linear function for the mean, which the linear function is taking these two conditions. So now we have this kind of the two conditions here, making some kind of the some affine function in terms of like having this kind of the linear weights and some kind of the constant here. So then we can define the linear functions as we want, but how should we also define this kind of the here the weights for the omega 0 and omega t and the p? So there can be some multiple ways that we can define the specific the conditional distribution. But we are going to somehow define this specific distribution in a way that we can still make sure that this forward jump distribution remains the same as the DDPM. So this is basically the key idea of the DDIM. So in the DDPM, we basically have seen that the forward jump, the posterior distribution, sampling the xt from the x0 was defined into basically this Gaussian form, right? This, right? So the basic idea of the DDIM is that while we are basically switching the forward process, we are also going to define this distribution in a way that we can maintain this posterior distribution to remain the same. So how we can do that? So basically we are going to use some kind of the induction, the idea. So basically some kind of the induction, we can basically see that. So let's assume that this the posterior distribution from the the x0 to the xt is defined into this Gaussian form. Then how should we define that this kind of 3D parameters in terms of that the posterior distribution for the xt minus 1 also is defined in this way. So if we can basically define these three parameters for this specific case for the time step t, then from the induction we can basically assume that like for all the time step t, this forward jump distribution is defined into this Gaussian form, right? So let's think about like how we're gonna derive this. So basically, we first need to see the connection between this, the conditional distribution with this kind of the two posterior distributions for the xt and the xt minus 1. And from the marginalization, we can see that the distribution with the xt minus 1 is now defined into this form, right? So this is nothing but just like simply marginalization, taking the xt and the xt minus 1 here, while taking the xt as the condition here. Right? So if you basically ignore the x0 here, then you can see that this is exactly the same form of the marginalization, nothing special that we have seen in like lecture 3 or so. And I'd like to show some like also one interesting kind of thing. Without some kind of the proof here, what we can also derive is that if we have like some kind of the prior distribution as kind of Gaussian form here, and also another some kind of the likelihood distribution as another the Gaussian form here, then this kind of the the marginal distribution now can have some another Gaussian distribution in this form, right? So this is basically the known fact without the proof. And you can also check out some kind of some reference for like into how we can exactly define this. But you can basically this is basically not complicated into like having just like 3 Gaussian distributions. So basically using these two facts, like we are having this kind of like the form of the marginalization and having this kind of form of like having the Gaussian distribution here. Can we also describe this posterior distribution for the xt minus 1 with respect to the omega 0 and the omega t and the p? And from this, since we know this Gaussian distribution, once we basically represent this distribution with respect to these 3 parameters, now we can define basically these 3 parameters into the other parameters that we have, right? So using these 2 key facts, let's try to basically derive these 2 things. So I'll give you like 10 minutes to basically try to solve this problem. So if you didn't download the slides yet, I recommend also download the slides and check out these 2 key the hints in the previous slide. Okay, so if we move on to the answer for those questions, so you can basically try to solve these problems using the hints in the previous slide. And you can see that now this distribution is now also can be described into this form, basically having these like 3 terms. And then based on the fact that like the mean and the variance are basically defined in 3, now we can derive the omega 0 and the omega t and the p here. And we can see that p just becomes 0 and the omega t and the omega 0 are basically defined this way. And from this, now we can, we can see that if we define this conditional distribution into this form, then we can basically say that the distribution for the fourth jump remains the same with the DDPM. So this is kind of like interesting effect. So basically, if we define the distribution, like sampling the xt minus from the xt and the xu into this space form, then also the interesting thing is that whatever the variance that we have here, so without like any kind of dependency with some kind of the definitions of the variance here, whatever numbers that we have for the variance, we can see that this specific form of this kind of the posterior distribution basically guarantees that the distribution for the fourth jump remains the same as the DDPM. So basically the difference with the DDPM and the DDIM is that in the DDPM, we defined the transitional distribution sampling the xt from the xt minus 1. And based on the definition also like this, now we could derive these 2 distributions, like these 2 the posterior distributions. The difference between the DDPM and the DDIM is that now we are not defining the full transitional distribution, but we first define this distribution, the xt minus 1, sampling xt minus from the xt and the xu. And based on the definitions of like this, now we can derive the distribution of like this fourth jump and the fourth transitional distribution. And the thing is that if we define this distribution as shown in the previous slide, then the fourth jump distribution remains the same with DDPM. So this is kind of the interesting effect. And also kind of the thing is that, as I mentioned in the previous slide, we can set any of the variance here, which means that we can also set 0 for the variance. So if we set 0 for the variance, this means that this becomes like just sampling the mean every time. So there is no any kind of stochastic. We already sample the mean here. So that can be basically the way that we can make the reverse process as kind of the not the stochastic process, but as kind of a deterministic process. So the thing is that if we start to basically define the distribution in this way, then we can now consider making the reverse process as kind of like deterministic. So let's get into some more details here. So the thing is that even when we basically change the fold processing that way, our the available function basically remains unchanged from the DDPM. So which means that we can still try to basically learn this kind of the variation of the likelihood distribution while minimizing the same loss function as the DDPM. So what we are also going to do is that we are also going to either predict mean or the x0 or the noise for the likelihood distribution. The question here is that so if you go back to previous slide by just downloading slide yourself, DDPM sigma t was predefined, but I'm confused that then just sigma t to 0. Yes, so that's kind of the difference. In the DDPM case, the sigma t was kind of the predefined, and now we can consider like the varying the sigma t as we want. So that's kind of the interesting part of the DDIM. So in the DDIM, but also the thing is that we can still basically run the reverse process by running the same type of the variation of the likelihood distribution, and even the loss function to train this kind of parameters for the likelihood the variation of the distribution is the same. So the answers for the quizzes will be posted. I will update the slides after the lecture. Obviously, I'm not posting the answers before the lecture. So basically, the thing is that while we are basically changing the fold and reverse the processes, we can use the same noise predictor or same mean predictor or same x0 predictor. So that's basically a very interesting effect. So even when you basically switch the diffusion model, the process from DDPM and the DDIM, we can still use the noise predictor, which was trained for the DDPM. Which can be directly applied for the DDIM, the reverse process. So which means that whatever we want to use the DDPM or the DDIM, actually we can use the same noise predictor, which is trained using the same the loss function in the previous slide. But while we are basically having the same the noise predictor, basically the reverse process and the fold process, the fold processes are basically changed. So in the DDPM reverse process, the fold process was like this. So basically this, the conditional distribution sampling the xt minus 1 from the xt and x0 was defined in this way. So, and the function was basically in the training was to basically match the likelihood distribution with this kind of the conditional distribution. Which means that if we have the noise predictor, from this, we get the kind of the best prediction of the x0 here. And based on the xt and the x0, we compute the mean of this distribution like this. And based on that, we can make a sample from this specific Gaussian distribution, right? And now we are switching this into the another distribution, the DDIM. So we are having another the Gaussian distribution for the same distribution here. And then using same the noise prediction network here, and then get some kind of prediction of the x0 here, and then compute the mean of this distribution, and then basically use the this mean and the given the variance to sample the xt minus 1. So you can see that the only difference is basically switching this distribution into this distribution, while basically using the mean, computing the mean using the same the noise predictor. Does it make sense? So then what's the meaning of like having this DDIM? Actually, the interesting thing is that this DDIM was basically a generalization of the DDPM. So actually we can make the DDIM to be the same with the DDPM by setting the variance to be the same variance of the DDPM. So it depends on like which variance that we set in the perturbation step. But if we set this like variance to be the same with the variance of DDPM, then we can see that actually
the one of the special case of the DDIM becomes of the DDPM. So for this specific case that we set the variance to be the same with the variance with DDPM, we can see that now the DDIM operates as some kind of the Markovian process. But by basically setting some kind of the different variance here, we can make the DDIM process as kind of the non-Markovian process. It is clear? So now we can see that like DDPM, DDIM are not the kind of the different diffusion models, but you can consider like DDIM as kind of some, as a like generalization of the DDPM process. So which means that now we parameterize this variance, this sigma t as kind of like this form. Then we can consider either making the reverse process as kind of like deterministic process by setting this to be 0. So if we go back to the reverse process of the DDIM, we can basically have this kind of process like adding this kind of the Gaussian noise with some kind of the by taking the variance as kind of the weight, right? So if we make this to be 0, then there is not some kind of the perturbation that we are adding in the reverse process. But we always take the mean, right? So which means that once we basically start from any kind of x capital T, the final the output x0 that we're gonna get through the iterative process will remain the same because there is nothing that we are adding some sort of the some noise here. So which means that the reverse process becomes deterministic. Like given the same x capital D, we can always get some kind of the same x0, right? Or we can make this DDIM process to be the same by setting this parameter to be 1. So this is also another special case that we are basically making the DDIM to be the same with the DDPM, right? And then why we are also talking about the DDIM? So we are actually talking about some kind of the pros and cons of the diffusion models. The downside of the diffusion model was that we basically need to iterate the reverse process, which is taking a lot of the time. So here the question is that how we can also reduce this kind of the computation time. So we can actually consider like skipping some of the time steps in our the reverse process, basically having some kind of the intervals in our the time domain and jumping over some kind of some time steps. And we can basically have, so this is kind of the case of like reverse process with the full sequence of the time steps. And instead of that, we can consider like having some kind of a subsequence of the time steps, like taking some intervals and the samples of the time domain, and then running the reverse process with this kind of subsequence of the time domain. And even when we run the reverse process in this way, still the L the objective function remains the same, which means that we can still use the same noise predictor for this kind of like subsequence of the time domains. But obviously, the thing is that as we basically decrease the number of the time steps, the quality of the outputs will be basically get worse. The thing is that if we also make the diffusion process as kind of the deterministic process, we can see the results that the quality degradation becomes like mitigated even when we basically decrease the number of the time steps. So let me quickly go over into this kind of some results here. So what we are basically seeing in this table is that we are seeing the kind of the FID scores that you also need to report in your the first assignment, which is basically lower is better. So as we see the lower score, which means that the quality of the output is better, right? And we are getting all the results basically while basically varying the stochastic, basically the weights for the parameters, for the variance, and also the number of the time steps here. And what we are seeing is that when this eta is 1, this is the same case with the DDPM, right? So in the DDPM case, as we decrease the number of the time steps from the 1000 to the 10, we can see that FID basically increases a lot, which means that the quality of the output becomes really bad, right? But if we make the generation, the process to be deterministic, basically making this eta to be the 0, then you can see that even when you basically decrease the number of the time steps from the 1000 to 10, actually the FID does not increase that much compared to the DDPM case, right? So which means that we can still like consider decreasing the number of the time steps while still maintaining some kind of better quality of the outputs. And even the thing is that when you use the full time step, like 1000, even the quality is still kind of like better than the case of the DDPM. So like long story short, the conclusion is that if we want to basically do some kind of the faster generation, while basically achieving still kind of good quality of the outputs in the generation, what we can do is that we can consider not using the DDPM, but using the DDIM, while basically making the process to be close to the deterministic, the process, like decreasing the parameters, the weights for the stochastic for the variance. And we can see that DDIM is basically some kind of the generalization of the DDPM. That's also what you basically we need to implement in the assignment tool. Any questions on this? So in this coming Wednesday, we're gonna get into some more details about the DDIM, and also our TA will also explain more about the assignment too. So also the Wednesday session will be a hybrid session. So please come join the offline session in the annual building. So I will see you on Wednesday. Okay. Bye.
Professor, can you see the question I've written in the Zoom, please?
June. Yes. Okay. The fact that using the subset of T doesn't worse the quality of the DDI improvement or is it normal? Yeah, so if we make the deterministic process, like why the quality gets better. So there is no some kind of a theoretical guarantees. It's more so about some kind of experimental kind of the empirical the outputs. But we're
thank
gonna also discuss some more details about this when we also discuss the stochastic differential equations. What is the cone of the using the deterministic reverse process? Well, I mean, yeah, there is no cons of the using the deterministic reverse process. So actually, in most of the cases, it's better to make it as kind of the more deterministic. So we're gonna also get into some more details about this. Any other questions? So if you have any other questions, please post the questions on this side. So, and I will see you on Wednesday. Bye.